Good morning, subscribers, and if you're not a subscriber, please subscribe to this YouTube channel. So today we're going to be going over the test for EGM 211. That's EGM 211. That's engineering mathematics. And then to introduce myself, I'm the A plus ambassador. Let me just abbreviate it like that, or you can call me the Universal Data Boy. So today we're going to be going over test 1, and then question 1 was on L'Hopital's theorem. It has different pronunciations, but then this is how you pronounce it. Others can say a hospital, potato, potato, anyway. Yeah. So, but to answer the question that's on question 1, first we have to revise L'Hopital's rule. And then after revising this one, can we be able to fully understand and grasp the questions? Because the rule works for when you have a function such that when you evaluate the limit, or when you input the values that are on the limit, you are going to have something undefined. So first of all, we're going to describe situations in which you can have something undefined, so that you can know when to apply this. Because these are situations where it's not applicable. For example, when something is coming out as 1 to infinity, you cannot. Yeah. So I think we can wrap this. So I'm going to give the scenarios in which you can use L'Hopital's rule. So for the first one is when you have something like infinity over infinity. For the second one is when you have the limit coming down to 0 over 0. Okay, the fourth one, or the third rather, is something where you're having infinity minus infinity. For the fourth one, so you're having something to the power infinity, maybe 1 to the power infinity, 2 to the power infinity, or even infinity itself, infinity to the power infinity. They can be such. What if you have maybe something like the limit as x approaches infinity of x to the power x, then you're going to be forced to come to something like this. And then on 5 rather, on 5 you're going to have maybe things like 0 times infinity. And then also other things, maybe if there are more, I'm going to tell you, but these are the general scenarios in which you can use this rule. So now, for the first one, you have infinity over infinity, so it's actually undefined because you don't know which value to come to. And then 0 over 0, when you have any number that where you have that's dividing by 0, you have undefined number because you don't know how many times that 0 goes into that number. And then for this one, you don't know this very big number and this very big number, if they subtract themselves, or are they going to dot down to 0, or are they going to side with the other big number? And then when you have things like this, you don't know what it will come to, because this number is like very, very big. And then this one as well, because infinity is a very, very big number. So when you multiply 0 by infinity, does it become 0? Does it become infinity? You actually have something that's basically undefined. So I'm going to, this is just a skeleton. So maybe for things like this one, you can even have something like maybe infinity, maybe it's dotting down to 100 to infinity. You still use the same principle. It's not that this principle only applies to things that are like this, but things that are similar to this. So now what happens when you have this, when you have such limits, is you cannot evaluate the limits because you don't know the value of. So what you're going to do is you're going to use this rule. Right? Yeah. So in any of these scenarios, we use L'Hopital's theorem, and then how it works is that if you have a function, the rule is this: if you have a function x as x approaches a of f of x, where f is a function of x, of course, and maybe h of x, and these are basically arbitrary, and you can use any for these. You can use j of h as long as it's a function of x, and then they are differentiable. And then when you have this, when you evaluate the limit as x approaches a of f prime of x, that's the first derivative, and the derivative of the denominator, again, this is going to be equal to that, as long as you evaluate to the same limit, and these are the same functions, and you differentiate both of them. So it works only for quotients. So now the problem comes in when you have things like this, and then I'm going to show how you can manipulate the rule when you have things like infinity minus infinity, or 0 times infinity, you're going to manipulate it in such a way that it's going to become a quotient and actually apply the rule, because the rule only works for quotient. Yeah. So now, for this one, I want you to keep in mind, because as we are doing this, all your questions will have things like infinity and 0, so you have to know when you have a 0 and you have infinity. So now, when you have something like natural log of infinity, the answer will be infinity. When you have natural log of 1, the answer will be 1. When you have exponent to the 0, the answer will be simply 1. When you have cosine 0, the answer is 1. Then sine 0, the answer is equal to 0. The example, if we have something like the limit as x approaches 0 of sine x over x. Now when you evaluate this function, you're going to find that you're going to have 0 over 0. See how this one kicks in, eh? Then this is undefined. So I'm going to find the derivative of this one and the derivative of this one. So the limit as x approaches 0 of the derivative of this one is the derivative of sin x is simply cos x, and then the derivative of x is simply 1. So now if you have problems with this, I've done another video that simplifies how you can memorize the derivative of fixed functions and also the integrals as well. So now when you evaluate now, you're not going to have anything that's undefined according to what we listed here. So when you evaluate 0 there, you're going to have cos 0. Well, this is just 1, so we can actually neglect it, because 0 is just equal to 1. Now since we have I would say basic understanding of what's going on, we can answer a test question. And then remember, since when you find the derivative of a function, when as x approaches a certain value, maybe as x approaches a of this function, you're going to have this one. And then for this one, you can apply the L'Hopital again and then differentiate it. So what I'm talking about is having something like the limit as x approaches a of the second derivative of x as h prime, h2 prime of course, approaches x. So it's like you can keep on finding the derivative because you keep on applying this rule. So now we go to the test question so that we can review question 1a. Question 1a. The question in the test was the limit as x approaches 0 of, it was already in quotient form, so makes things easier for us. Sine 2x plus 7x squared minus 2x, then it was over x squared x plus 1 squared. So now, as it stands here, when you evaluate x there, you're going to have zeros on top here, because 2 times 0 is basically 0. Sine 0 is 0. This one is definitely a 0. There is a 0. And then here, it's not a 0, because we have the 1 there, but then it's being multiplied by x to the power 2. X, when x is 0, the entire thing becomes 0. So here, we have 0 over 0. And then you can actually explain this in your calculations to say both are 0, so they are undefined. So here, we are going to apply L'Hopital's rule depending to what exactly your teacher wants. If your teacher wants a lot of explanations, if he's someone who only wants the answer, then you can just peruse through. Especially in situations whereby you're in an exam, you have a lot of questions, you can't do explanations. You just do a quick one because the sir definitely knows that you know. So now, for this one to make it easier, I'm going to evaluate this, because this is just, we have to go through everything now. Plus 7x squared minus 2x x squared over x plus 1 times x plus 1. That's this one. Never be forgetting the limits. I'll put them at the end anyway. So sine 2x plus 7x squared minus 2x over x squared. Then now in here, x times x is x squared. X times 1 is x, then 1 times x is x, so we're going to have the 2x there, then 1 times 1 is simply 1. But then it's being multiplied by all this. So we haven't yet started differentiating, by the way. We're still on the easy minus 2x. Make sure I put in the limits inside. So when this multiplies by that, it will be x to the power 4 plus 2x to the power 3 now, and then plus x to the power 2. So now this is will still equal to 0. So now this is where we start our differentiation. We can even say applying L'Hopital's rule. Now we start differentiating. This is the limit as x approaches 0. So you find the first derivative. So the derivative of sine 2x is 2 cosine 2x. So plus this one is simply 14. This is basic calculus, and I don't need to go over this. This is 4x to the power 3 plus 6x to the power 2 plus 2x. So now when you evaluate the limit, we're going to have a 2 on top, but then a 0 on the bottom. So we continue. You say the derivative of this one will now be 4 because of these 2 and the other 2, sine, and now it's negative. This is a 4, by the way. Now it's negative 2x plus 14 all over 12x to the power 2 plus 6x. Well, this is 12 plus 12 again, 12x plus 2. So now you can evaluate this one without having something that's undefined, and then you can have, this is the limit, and I'm only forgetting to put the limits to make this video as short as possible, but you have to remember to always put them. So when you evaluate the limit now, you're going to have negative 4 sine 2 0 plus 14 over 12 0 squared plus 12 0 plus 2, which is equal to 14 over 2, which is equal to 7. And that's your answer. You've evaluated the limit of all these quotients as x approaches 0 using the L'Hopital's rule. So that's the question that was in the test and the solution. That was question 1, Roman numeral 1. So now we are going to go to question 2. The limit as t approaches infinity of t, is it? Of t in brackets natural log of 1 plus 3 over t. Well, when you initially look at this one, you think we don't have to apply the rule. But then when you remember one of those times that you can apply this one, you're going to see how it comes into play. Because when you evaluate this one, because at first try to evaluate the limit, you're going to have infinity for t, you're going to have infinity, then the limit as, this is 1 plus 3 over infinity. So infinity over any number is basically 0. So we're going to have natural log of 1, since this will become 0. So now the natural log of 1, as I said, is simply 0. So now you have infinity times 0, so you don't know the number that you're going to come to. So you cannot evaluate this one. This one is undefined. So now what you're going to do is apply L'Hopital's rule. So in the next video, I'm going to explain how you can now apply L'Hopital's rule in a situation when you have something like this. So stay tuned to the next video so that you can see the explanation on how you can apply this one.